Hello and welcome back. In this video, we're going to learn about empirical and molecular formulas. So let's first define what empirical and molecular formulas are. We'll start with empirical formulas. Empirical formulas give the smallest whole number ratio of the atoms that are present in a compound. They don't necessarily represent a molecule, but sometimes they do. Molecular formulas give the specific number of each type of atom that's present in that molecule. Molecular formula is equal to the empirical formula times a whole number n. So the molecular formula is a whole number multiple of the empirical formula. So let's go ahead and look at some examples. So the molecular formula C2H2 and C6H6 both have the empirical formula CH. Notice that these are molecular formulas because they represent the actual compound. They give the specific number of the type of atom that's present in that compound, whereas the empirical formula is the simplified formula of the molecular formula. Now, sometimes, like in the case of H2O, the molecular and empirical formulas are the same. So in this case, the empirical formula does actually represent the molecule, which is the molecular formula as well. All right, so let's go ahead and look at how we would actually calculate the empirical formula from given experimental data. So in this example, we have an oxide of nitrogen that contains 0.5433 moles of nitrogen and 1.087 moles of oxygen, and we want to determine what the empirical formula is for this substance. So first of all, the empirical formula would have the structure N, say X, O, Y. So our goal here is to find the value of X and Y. Remember that in order to find the empirical formula, X and Y are ratios of each other. They're whole number ratios of each other. And they're actually mole ratios of each other. So what we would do is we take our 0.5433 moles of nitrogen and we take our 1.087 moles of oxygen, and we determine what that mole ratio is. To determine the mole ratio, we divide both of our moles by the smallest mole value, which in this case is the 0.5433. So we divide both of them by that value, and that'll give us the mole ratio. So in the case of the nitrogen, that number will equal to 1. And then in the case of the oxygen, that number will equal to 2. Calculator gives me 2.000, so that's a 2. So if I were to write this formula, I would replace X with 1, and I would replace Y with 2. And remember that in a formula, we just leave out the 1, the subscript 1. So this would be NO2 as its empirical formula. So now let's go ahead and go over the rules for calculating empirical formula from experimental data. First, we want to write or compute the masses for each of the element that's in a sample. We're not always going to be given the moles of the samples. Sometimes we'll be given grams of some samples, and sometimes we're going to be given percentage of samples. If we're given grams of samples, then it's fine. We would just have to first convert them to moles. If you're given percentage of the samples, assume that you have 100 gram sample total. It's okay to assume 100 grams of sample because remember, we're looking for ratios. And so it'll still give us the ratios if we just assume there's 100 grams of sample. So if we assume there's 100 grams of sample, all we do is just convert the percentage into a gram. And then we're going to convert each of the masses to moles using the molar mass as a conversion factor. And then the rest is just like the problem we just did. You divide each by the smallest mole, okay? And then if all of them are not whole numbers, you should get all whole numbers, but a lot of times you will not. then you will have to multiply all the numbers by a factor that will get rid of the fraction or make everything a whole number. And then you write a formula using the final numbers as subscripts. All right, so let's go ahead and look at this example. A compound contains 25.94% nitrogen and the rest oxygen by mass. What is the empirical formula of the compound? So notice that here we're only given the percent mass of one of our substances, not both of them. The two, though, add up to 100%. So if we know that the nitrogen is 25.94%, then we know the oxygen is 100% minus the 25.94% because the two together add up to 100%. That means we have 74.06% oxygen by mass. So the formula we're looking for is just like the one before. We're trying to find the values of X and Y in this formula. Remember that in the rules, it says that if you're given percentage, just assume you have 100% of the substance. So we're going to assume that we have 25.94 grams of nitrogen and that we have 74.06 grams of oxygen. So really all I did was just to convert the grams or the percentages into grams. And then I'm going to convert the grams into moles because the X and Y values here, these here are mole ratios. And so I need to find the mole ratios, so I have to convert the masses into moles. So I use the molar mass of nitrogen from the periodic table, which is the bottom number in the periodic table. And for nitrogen, if I do 25.94 divided by 14.01, the answer comes out to 1.852. So I want to carry at least the same number of significant figures that I'm given here. I have 4 sig figs here, so I want to have at least 4 sig figs here as my answer. I do the same thing for oxygen. I use its molar mass, which is 16.00, and I convert it from grams to moles. So if I take the 74.06 and divide that by the 16.00, the calculator gives me 4.629 moles. And then remember, we're trying to find the mole ratio, so we divide by the smallest mole. The nitrogen mole is smaller, so we divide both of them by 1.852. I divide this one by 1.852. Here, this just comes out to 1. And then for the oxygen, I get 2.499, which is basically 2.5. But notice that these are not whole numbers. These are fractions. So what I need to do is I need to multiply both of them by a number that gives me a whole number. If I multiply both of them by 2, I get 5 here and I get 2 here. So my formula comes out to N2O5. So the oxygen subscript is 5, so the Y value is 5, and the X value is a 2. Here is another one to look at. Given the mass composition below, find the empirical formula. Notice that in this case, the compound that we have has 3 different elements. So I need to find 3 different subscripts. So this would be the formula, and we need to find the values of X, Y, and Z. Remember or notice that these 3 percentages have to add up to 100%. Okay, otherwise it would not be correct. So we assume, because we're only given percentages, we assume that we have 100 grams. So I'm going to assume that there's 63.15 grams of carbon. There is 5.30 grams of hydrogen, and there's 31.55 grams of oxygen. And then again, we're going to convert each of these masses into moles using the molar mass from the periodic table. Carbon has a molar mass of 12.01. Hydrogen has a molar mass of 1.01, and oxygen has a molar mass of 16.00. So when I plug this into my calculator for carbon, I get, again, remember I want to keep the significant figures as what I'm given, so I get 5.258. For the hydrogen, this comes out to 5.248. And for the oxygen, it comes out to 1.972. Again, remember we divide by the smallest mole. The 1.972 is the smallest of all of our moles. So we divide all of them by 1.972. So then for the carbon, the answer comes out to 2.666. And then when I divide for the hydrogen, I get 2.661. And when I divide for the oxygen, I get 1. Notice that 6 is about 2/3, right? 0.66. So this is about 2 and 2/3. So I know that if I multiply this by 3, it'll give me a whole number. Same thing up here. I multiply all of them by 3, and I end up with 8 as the carbon value, 8 for the hydrogen value, and 3 for the oxygen value. And so that's the empirical formula. So to know which number to multiply by, you can just start with, 2, 3, 4, 5, and just going through the numbers and see which one gives you a whole number. Or you can just remember that if it ends in 0.20, 0.20 is the same thing as 1/5, so you multiply by 5. 0.25 is the same thing as 1/4, so you multiply by 4, right? We multiply by whatever the denominator is to get rid of the fraction or decimal. 0.33 is 1/3, so we multiply by 3. 0.50 is a half, right? So we multiply by 2. 0.66 we just saw is 2/3, we multiply by 3. 0.75 is 3/4, we multiply by 4, and 0.80 is 4/5, so we multiply by 5. So you could either memorize these numbers or just play around, by multiplying by 2, 3, 4, 5. Eventually, one of those will come out to a whole number. All right, so now let's go ahead and look at how we would calculate the molecular formula if we were given empirical formula. So remember that the molecular formula is equal to the empirical formula times a whole number n. This means that the molar mass of the molecular formula is equal to the empirical formula mass times the value n. So if we know the molar mass of a substance and we know the empirical formula, we can find the molecular formula. So let's look at this example here. What is the molecular formula of a compound that has empirical formula HO and molar mass 34.02 grams? So first what we do is find the molar mass of this empirical formula, which is the hydrogen with a molar mass of 1.01 grams per mole plus the oxygen, which is 16.00 grams per mole. Remember, this is the bottom number from the periodic table. So this comes out to 17.01 grams per mole. And then remember we said that the empirical formula molar mass, or the molecular formula molar mass, which is 34.02 grams per mole, divided by the empirical formula molar mass, gives us the value n, which in this case will equal 2, which means that if I multiply the empirical formula by 2, that would give me the molecular formula. All right, so here are some practice problems for you to try on your own, and then on the next page, you will see the answer key. So you can pause this video, try these problems, and then look at the answers. And here are the answers to those problems.